Okay, so I'd like to thank again IMS and the organizers of the conference for inviting me to this excellent place. So today's talk will be on analyticity in superstring loop amplitudes. Okay. And although my goal will be to analyze string amplitudes, we will see that the techniques that we'll be using are all borrowed from quantum field theory. Okay, so there will not be really that much of string theory in this talk. Okay. So let me begin by stating the problem that we will try to address. Okay. So let's consider a scattering amplitude of n particles. We'll denote the moment of these particles by PA, where this index A will run from 1 to n. Okay. And they, of course, will satisfy the on-shell condition. Okay. I'll take all the masses to be positive, so for now, no massless particles. Okay. I'll talk about massless particles a little later. We'll also use the convention that all momenta will be taken to be ingoing. So if there is an outgoing particle, it will have negative energy. Okay, that's the convention. And we'll be using mostly plus signature, so PA square is given by this. So now, suppose we define the Mandelstam variable SAB, which is minus PA plus PB square. Okay. Of course, not all of these SABs are independent because of the mass cell condition, but let's take the independent Mandelstam variables. And the question that we want to address is in what domain in the complex SAB space the scattering amplitude analytic. Okay, that's the question. And the reason that we want to address this is because this result is a useful starting point for studying many other properties, okay, like crossing symmetry or dispersion relations and so on. Okay, so the domain of analyticity of S matrix. So let me first briefly recall how this is normally studied in quantum field theory, okay, or at least how it was studied in quantum field theory in the old days. So let's consider the off-shell amputated Green's function. So the external propagators are removed, which I'll denote by G, and I also assume that G includes all the wave function normalization factors. Okay, so that the S matrix is just given by G evaluated on shell. Okay, so you take this function G, which is evaluated off shell, and then set external momenta to be on shell, and that's what gives the S matrix. Okay. And here, just for simplicity, I have dropped the Lorentz indices, but I mean, our analysis that we'll be describing is valid for also particles with spin. Now, let's suppose we define A alpha to be some subset of these numbers 1 to n. Okay. It's a proper subset, so it doesn't include the empty space or the complete set. And we define P alpha to be the sum of the momenta PA with A lying in this subset. Okay, so there are sum of momenta of a subset of external particles. Now, this is a result that is a starting point of the whole game. Okay. I'll not prove this result, but the way it's proved is basically you start by using the locality of the position space Green's function, okay, which means for the position space Green's function, you know, for example, that certain combinations vanish because the commutators outside the light cone vanish. Okay. And starting with these identities in the position space, okay, one can show that the Fourier transform, okay, is analytic in a certain domain, and this is a domain. Okay, this is the important domain of analyticity. So if P alpha is complex, that means if imaginary P alpha is non-zero, okay, then it says that imaginary P alpha is time-like, okay, or null. Okay. If imaginary P alpha is 0, that means if P alpha is real, okay, then it requires that P alpha must be less than the threshold of production of any multi-particle states. Okay, so that's what this condition says. This basically says that if we take the total momentum P alpha, okay, it cannot be thought of as a sum of momenta of a set of on-shell particles, okay, which are all outgoing or which are all incoming. Okay. So what one can show just based on the locality of the position space Green's function is that the Green's function is the momentum space Green's function is analytic in this domain. Okay, and we'll see this domain many times in the next few slides. Okay. So this is the statement, okay, and we'll call this the primitive domain of analyticity. Okay. Now we'll prove a result which is somewhat discouraging, okay, at least on naively. Okay. And the result is that this domain has zero intersection with the subspace in which the external states are on shell. Namely, that if we demand that this condition holds, and if we demand that all the external particles are on shell, okay, then there is no intersection. There are no common points. Okay. And the proof is reasonably simple. It's kinematics. Okay. So let's take the momentum of an external particle, okay, and we denote by PAR the real part and the PI the imaginary part of that momentum. Okay. Then the on-shell condition is PA square equal to minus MA square. Okay. On the other hand, PA square we can expand out. Okay. And because MA is real, both the imaginary part must vanish. So PAR.PI must vanish. Okay. And this in turn implies that either PAR or PI must be space-like. Okay. Because if we take two time-like vectors, okay, then their inner product never vanishes. Okay. If there are two time-like vectors, both are future pointing or both are past pointing, then their inner product is always negative. Okay. If one is future pointing, one is past pointing, then the inner product is always positive. Okay. So at least one of these must be space-like. Okay. Both can also be space-like. Okay. Now, if we look at the real part of this equation, okay, then we see that this implies that Pi square is positive. Okay. So Pi is space-like. This is in contradiction to the first condition, okay, which says that for any subset of the external momenta, the imaginary P alpha must be time-like. Okay, so it's certainly in conflict with this. So that basically means that if we want to intersect this domain, okay, all the P's must be real. I hope this is clear. Okay, it's just simple kinematic analysis. But if all the P's are real, then P alpha is real. Okay. But now you see that this is in conflict with the second condition, okay, because if P alpha is real, then of course imaginary P alpha is 0. Okay. But now we know that it cannot be that for every set we are below the threshold. Okay, because after all, a scattering includes certain incoming states and certain outgoing states. Okay. Just takes a set of all the incoming states, which are all carrying real momentum. Okay. You can certainly produce those same states back again, right? It's without violating any conservation law anywhere. Okay. So it's already above the threshold. Okay. So that shows that it's in conflict with the second condition. So the apparent conclusion that we will draw from here is that the analyticity of G in the primitive domain that follows from locality of the Green's function, of the position space Green's function, is useless for exploring analyticity properties of the S matrix because there is no overlap between these two domains. So the way out, okay, which of course was found in the 60s and 50s, okay, is the following result. Okay. Then let's suppose that we have a function, okay, which is an analytic function of multiple complex variables. Okay, this is specific, this result that I will be describing is specific to the function of multiple complex variables. It doesn't hold for a function of single complex variable. Okay. So let's suppose that we have a function of multiple complex variables and we know that this function is analytic in some domain D. Okay. Then often, without knowing anything else about f, okay, we can prove that a function is analytic in an extended domain D prime. Okay. And we can find D prime purely in terms of D, okay, without knowing anything else about the function. So D prime depends on D, but not on F. Of course, the actual analyticity may be even larger. Okay, we don't know whether the actual domain of analyticity is larger, but just based on the knowledge of D, we can get some D prime. Okay, typically, of course, it may happen that the D is such that you cannot extend it any further. Okay. This is unlike function of one complex variable because we can, given any domain in complex plane, we can cook up functions of one complex variable, okay, which is analytic inside, okay, and has no analytic continuation across the domain, across the boundary. Okay, for example, Young's edge singularities are of this kind. So again, I will not give the proof, but here is an example. Okay, how you can extend the function. Okay. So let's suppose that we have a function of two variables, okay, and it's known to be analytic in a domain which is the union of two domains, D1 and D2. Okay. So D1 consists of a product of a unit disk in the Z2 plane, okay, and an annulus around unit radius circle in the Z1 plane. And D2 is the opposite. Okay. It's known to be analytic. D2 includes an annular region in the Z2 plane and the unit disk in the Z1 plane. So given this, okay, D1 union D2 is, you can show, is a simply connected space. Okay. Given this, one can show that F is analytic in this bigger domain D prime, okay, which consists of the product of the two unit disks. Okay. And this is the way one proves this. Okay. So given Z1, Z2 in D prime, we define a function G Z1, Z2, okay, which basically includes the contour integral of F zeta 1 Z2, okay, over a contour. So the contour basically looks like this. So if it's in the Z1 plane, okay, so this is the zeta 1 contour, okay, it lies inside the strip in which this function is known to be analytic. Okay, so you integrate over this contour. Okay. So this is a perfectly well defined object because it uses F in the domain. It uses F in the domain where it's known to be analytic. Okay. And you can show that it agrees with F when Z1 and Z2 are in D2. Okay, because inside D2 you see in the Z1 plane is a full unit disk, which is a domain of analyticity, okay, already known. So we can, in D2, we can simply shrink this zeta 1 contour, okay, and evaluate this using Cauchy's integral theorem, and we can show that this agrees with Fz1 and Z2. Okay. So this means that we have now constructed a function Gz1, Z2, which is analytic inside D prime, okay, the product of the two unit disks, okay, and which agrees with F in D2. Okay. So this means that G is an analytic continuation of F in D prime. Okay. So that shows that you can analytically extend this function in this bigger domain D prime, okay, just by knowing that it's analytic here. Okay. So using this kind of argument, okay, one can extend the domain of analyticity of G beyond the primitive domain. Okay, and this is what was done in the early days of axiomatic quantum field theory. Okay. And what one finds is the extended domain includes points satisfying p square plus m square equal to 0, and hence we can say something about the S matrix, okay, satisfying on cell condition. And indeed this was used to prove various interesting results for 2 to 2 scattering and some for 2 to many scattering. Okay. For example, it was used to prove crossing symmetry, okay, which says that we should have an analytic continuation that relates A plus B going to C plus D to A plus C bar going to B bar plus D. Okay. So what is clear, okay, just from standard quantum field theory, is that the same Green's function determines both of these. Okay. But of course, the relevant kinematic variables take values in different range here and here. Okay. And crossing symmetry is a statement that there is an analytic continuation that relates these two kinematic domains, and this was proven by doing this extension by these people. Similarly, one can prove that the elastic forward scattering amplitude is analytic in the full complex S plane. Okay, and then there are various other statements that one can make based on these results. So the question that we'll be interested in is what happens in superstring theory. So we want to follow the same approach, and for that we need off-cell Green's function. So of course standard superstring perturbation theory doesn't tell us how to compute off-cell Green's function, okay, but we can use superstring field theory to define off-cell Green's function, okay, and then we can try to see if we can prove these results. Okay. Because see, once we have proven this, okay, then everything else that was done in the early days of axiomatic field theory will hold automatically, because these results, for example, follow from this, okay, without knowing anything else about the theory. Okay. It simply requires the domain of analyticity, and then it automatically extends the domain to this bigger domain. Okay. So if we can prove this for superstring theory, then we also have proven all the interesting results for the on-shell S-matrix elements in superstring theory. Now the problem here is that we do not have the position space Green's functions as a starting point. Okay. In superstring field theory, the position space Green's functions are not understood properly, okay, and in fact they probably have a very complicated structure. Okay. So the strategy is to try to prove these properties directly in the momentum space using Feynman diagrams. Okay. So the proof will be perturbative, it will be to given order in perturbation theory. Okay. But we simply directly examine the Feynman diagrams of superstring field theory and see if we can prove these results to a given order in perturbation theory. So that is the strategy. Okay. So let me say a few words about superstring field theory. Okay. The details are not going to be very important. Okay. And since we will be drawing Feynman diagrams, what we really need is gauge fixed superstring field theory. Okay. And here is a general structure of the gauge fixed action. Okay. So here phi alphas are the set of all the fields. There are infinite number of fields because of course superstring theory has infinite number of particles. Okay. So the gauge fixed action, okay, has the form of a kinetic term. Okay. This k alpha beta is a function of the momenta, and in general this is quadratic in momenta. Okay. So k alpha beta is nothing unusual for superstring field theory. What is unusual is the vortices. Okay. These vortices, okay, are complicated functions of momenta. Okay. They are arbitrary point vortices. Okay. But the property that all the vortices share, okay, is that these have exponential suppression factors. Okay. And these exponential suppression factors makes it suppressed as ki zeros approach I infinity and ki n's approach plus minus infinity. Okay. So basically the exponential suppression takes the form of e to the minus some constant sum over alpha k alpha square plus m alpha square. Okay, where m alpha is the mass of the particle and k alpha square is the invariant square of k alpha. Okay. So because of the, and c is positive, I should have said that. Okay. So roughly c can be taken to be of the string scale, okay, but different versions of superstring field theory will have different c's. Okay. So because of this exponential suppression, okay, what one can show is that each Feynman diagram in the theory is manifestly ultraviolet finite, okay, provided the Ks0 integration contours end at plus minus I infinity and the Ksi integration contours end at plus minus infinity. Okay, you can see from here that you have to choose that because of this minus sign that K0 square has. Okay, so as Ki, the spatial components go to plus minus infinity, this falls off. Okay. And as K0 goes to plus minus I infinity, again this falls off. Okay. This factor also shows that even though there are infinite number of particles, okay, the sum over those infinite number of particles also give a finite result, because the larger the mass of the particle, the smaller is a vortex. Okay. So everything is convergent and we can work with this, okay, for each Feynman diagram by Feynman diagram and study its singularities. So let me now come to the infrared issues. Okay. Again, it was known in the early days of quantum field theory, okay, that all these results on analyticity, crossing symmetry, etc., okay, are valid in theories without massless particles. Okay. Because once you have massless particles, okay, there are infrared singularities, okay, which have to be treated separately. Okay. And this is the same in superstring theory. It has gravitons, of course, all string theories have gravitons. Okay. Often it has photons. So the singularities that are associated with gravitons and photons, etc., have to be treated separately. Okay. And they will not be covered by the analysis that we'll be doing. Okay. So the way we can handle this, okay, accepting that these have to be treated separately, okay, there are two possible ways one can proceed. okay, what we will call either subtraction or regulation. Okay. So subtraction amounts to the following. Okay. We basically replace each internal propagator by 1 minus p, where p is the projection operator to massless fields. Okay. And the analyticity that we will be studying will be analyzed for this amplitude. Okay. Of course, this is not a full S matrix. The full S matrix will require putting by the massless fields and calculating their effects separately. Okay. But that part will be the same as in any quantum field theory. Okay. The infrared singularities that we will get in an S matrix will be in any quantum field theory with massless fields. Okay. So those have to be taken care of separately. One can also regulate. Okay. This is useful in dimensions higher than 4. Okay. Namely that one can simply add mass term for the massless particles in the gauge fixed action. Okay. So this regulated amplitude will be free from infrared singularities. Okay. And one can analyze analyticity for this amplitude. Okay. And furthermore, as long as the space-time dimension is larger than 4, okay, the regulated amplitude will approach the actual amplitude for small mass. Okay. So if you take the regulated amplitude and take the m goes to 0 limit, okay, you get back the finite results, which are the scattering amplitudes in higher dimension. Okay. But of course, getting finite result doesn't mean that it's analytic. Okay. Basically, the kind of singularities we will get of the are like x to the n log x. Okay. It's finite as x goes to 0, but of course, it's still non-analytic. Yes.
In terms of gravitons as well? Or
yes, even for gravitons.
I thought the critical dimension was more like 7 or something for gravitons.
I think the infrared, the soft divergence goes away after 4. If you do perturbation theory. Yeah, if you just do power counting, right? This is just a standard perturbation theory. So the power counting divergences go away after beyond 4. Okay. So basically, we will proceed by assuming that there are no strictly zero mass particles in the theory. Okay, because zero mass particles are either regulated away or they have been subtracted and have to be taken care of separately. Okay. So let me now give a brief outline of how we go about analyzing this. Okay. So we'll begin by analyzing this Green's function at 0 momentum, when all the external momenta are 0. Okay. When all the external momenta are 0, we take the loop energy integration contour to be along the imaginary axis, okay, and the integration contour for spatial components along the real axis. This is good because the convergence is ensured, okay, and it's also good because if we now take an internal propagator of momentum L, okay, because the external momenta are all 0, okay, and the loop momenta are chosen in this way, okay, L0 is always imaginary and Li is real. Okay. So L square plus m square is strictly positive, okay, because it's minus L0 square plus L square plus m square. So the integrals are perfectly well defined. There are no poles and it falls off at plus minus infinity. Okay. So this leads us to the conclusion that G is analytic in the neighborhood of Pa equal to 0. Okay. This will fail if there are massless particles, right? If the mass is 0, then this can still vanish along the integration contour. So here I have described pictorially the distribution of poles in a complex loop energy space plane. So let's focus on one particular loop energy integration. Okay. So this is the vertical axis is the imaginary K0, the real horizontal axis is the real K0. Okay. And in the K0 plane, okay, the poles are distributed this way. Okay, this is L0. So L's are the notation that we will be using is that L's will describe the momenta carried by individual propagators, and K will be the independent loop momentum integration. Okay. So L's are given by linear combinations of the K's. Okay. So the poles will be distributed symmetrically, okay, in the L plane, and in the K0 plane they will be also shifted vertically because of course this will be shifted by other loop momenta, okay, entering the various propagators. Okay, and we will see some examples of this later. So the idea is that we will start from this configuration, okay, where poles are all kept away from the integration contour, okay, and then we will see what happens when we deform the external momenta away from 0, okay, because the pole positions are going to move, Okay, eventually they'll come and hit us, hit the integration contour, and that's where the potential singularities will come from. Okay. From the infinities, there are no singularities because of the exponential suppression. So if we find that the poles are approaching the integration contour, okay, what we need to do is to move the contour away from the poles to avoid singularities. Okay. But the ends have to be kept fixed. Okay. Because this you cannot change. K0 integration has to end at plus minus I infinity, and the Ki integrals have to end at plus minus infinity because of this exponential factor. Okay, we have some leeway, we can rotate it a little bit, but not too much. Okay. And this is where the prescription differs from the field theory prescription, because in field theory you can rotate the contours. Okay. And for example, for real external momentum, we take the integration momentum integration axis along the real axis, okay, and use the Feynman I epsilon prescription. That you cannot do here, okay, because along the real axis the K0 integral will diverge at infinity. Okay. So you have to really keep the ends fixed at plus minus I infinity. Okay, so as the pole approaches the contour, you have to deform it, okay, which you can do, of course. It's a complex integral. Okay. So you don't really encounter a singularity in such situations. Okay. The singularities come when the contour is pinched by poles from two sides. Suppose you have two poles coming from two opposite sides, okay, and pinching the contour. Okay. Then, of course, you cannot deform it away. Okay. And then you have the possibility of a genuine singularity. Okay. Then that's the place when the integrand itself the integral itself becomes singular. Okay. So what we have to show is that this doesn't happen inside the primitive domain D. Okay. If we can show this, then that proves the desired result. Okay. That the Green's function is analytic inside the primitive domain of analyticity. So what we have been able to prove is not the most general result, okay, but a limited version of the statement. Okay. So what we have been able to prove is that this is true, that the Green's function is analytic inside the primitive domain of analyticity when the imaginary part of all the external momenta lie in a two-dimensional Lorentzian plane, okay, which we can take to be the 0-1 plane, but any other two-dimensional Lorentzian plane is good enough. Okay. So which basically means that all the imaginary parts of all the external momenta, okay, are given by just linear combinations of two independent vectors. Okay. Now this may sound like a strong restriction, and indeed it is a strong restriction. Okay. However, okay, this is sufficient to prove all the known analyticity properties of the S matrix that was proved for local quantum field theory. Okay. And basically the point is that while we know that the Green's function has this big primitive domain of analyticity, okay, as far as I know, nobody has been able to make use of that big domain of analyticity, okay, outside this two-dimensional plane. Okay. So all the proofs of analyticity or the study of analyticity is done based on, mostly in fact it's done based on having one independent vector, the imaginary part, all the imaginary parts being linear combinations of one independent vector. Okay. Some uses two linearly independent vectors, but nothing more than that. Okay. So in that sense, okay, this is good enough to prove whatever is known about S matrix in quantum field theory. Okay, although it will be nice to have a more general proof. So this is the end of the gong show, okay, the summary of the results. Okay. So in the rest of the talk, I'll see to what extent I can explain how we derive this. So what we do is to carry out our analysis in two steps. Okay. So you have to show that we can deform, that given any point, okay, inside the primitive domain of analyticity, okay, we know that the function is analytic near the origin. So you have to find some way to deform the momenta from the origin to the desired point, okay, and show that we don't hit singularities. Okay. So the way we carry out this deformation is in two steps. Okay. In the first step, we keep the imaginary part of the P1 for all external momenta to 0, okay, and deform all other components of all external momentum from 0 to the desired value remaining inside D. Okay. Okay. So in this part of the deformation, only the 0 component has imaginary part, okay, because of course we are allowing only 0 and 1 components to have imaginary part, and we are keeping the imaginary part of P1 to be 0. Okay. So the idea is that we will first show that during this deformation, we do not encounter any pinch singularity on the way. The second part is to deform imaginary P1 from 0 to the desired value, and in this step we are going to keep all other components fixed and we will remain inside T. And again you have to show that you do not encounter a pinch singularity during this deformation. So for simplicity we can imagine that we are doing this deformation along a straight line, okay, but that's not necessary. As long as we are inside D, any path will do. Okay. So this is a symmetric representation of this deformation in the imaginary PA plane. Okay. So the first step in the deformation is the imaginary PA0 is deformed to its desired value, and along the way we also deform everything else to the desired values. Okay. In the second step, we only deform imaginary P1A, keeping everything else fixed. Okay. So let me at least go through step 1 and then we will see how far we can go with step 2. Okay. So step 1, as I said, is to deform all components of PA other than imaginary P1A to the desired value, keeping this fixed at 0. Okay. Now, I should point out one thing here, that when we say that we want to prove the existence of a contour, okay, existence of any contour that avoids the singularities will do. Right? There will be many contours which avoid the singularity, but as long as you can show that it is possible to deform the contour in one particular way, avoiding the singularities, that's good enough for establishing absence of singularity. Okay? So we will make a choice of how we want to deform the contours. Okay? So the way we will deform the contour is the following, that we continue to integrate the spatial components of loop momenta, okay, all the spatial components along the real axis. Okay, because of course P equal to 0 is started along the real axis. But we will allow the Ks0 integration contours to be deformed, keeping their ends fixed at plus minus I infinity. Okay, so we will allow the Ks0 integration contours to be deformed like this, but all the spatial components will be integrated along the real axis. Okay. And the goal will be to show that the K0 contours are never pinched. And the way we will show this is to assume the opposite. Okay, we will assume that they are pinched, and then we will show that there is a contradiction. Okay, the contradiction will be with the fact that we are inside D. So let's suppose that we run into a singularity along the deformation. So the first time we hit a pinch singularity, certain internal propagators are forced to be on shell, right? Because whenever these singularities are after all poles of the propagator, right? So when two poles are coming close, that means that we cannot deform the contour away from these poles. Okay? So those propagators are on shell. So we'll associate with the pinch a reduced diagram, okay, which you obtain by shrinking to point all propagators that are not forced to be on shell at that point. Okay, so you basically focus on the singular part. Okay, we take the original graph, okay, and simply collapse to points all propagators that are not on shell, that are not forced to be on shell. Okay. We do something more, okay, that if we have a on-shell propagator carrying momentum L, okay, of course this is the on-shell condition, okay, and as long as M is non-zero, okay, only one of these can hold, okay, and depending on which one holds, we will draw an arrow along L if L0 is positive, that means if L0 is a plus square root of L square plus M square, and opposite to L if L0 is negative. Okay. So basically then the arrows, okay, so the inside the reduced diagram, the propagators that are displayed are the ones that are forced to be on shell, and the arrows on the propagators tells us which direction the energy is flowing. Okay, that's the simple statement. So here I have drawn a reduced diagram. Okay, this means that everything else, there may be, the original diagram may have had many more propagators. They have all been collapsed because they are not forced to be on shell. Now, the claim that we'll make is that the arrows in a reduced diagram cannot form a closed loop. Okay. So, for example, this is not an allowed reduced diagram because here you see the arrows form a closed loop. Okay. So, let's go through the proof of this. Okay, why this cannot be an allowed reduced diagram. Okay. So, let's suppose the K is the momentum along such a loop. Okay. And LR are the momenta carried by the arrow, carried along the arrow by individual propagators. Okay, so L1, L2, L3, as you can see. So the structure, the relation between LR and K is that LR must be K plus some capital LR, where this is determined with the external momentum and other loop momentum. Okay, this depends on how much momentum is flowing through this vortex. Okay, but there is always an additive K, okay, because you have labeled the L's along K. Now, if we go back to our original picture, okay, there is a trivial observation from there which is going to be useful. If you look at this, okay, you see that, so K adds to L, right? So this you can also think of as a K integration contour. Okay. That all the poles with L0 positive are on the right of this integration contour, all the poles with L0 negative are on the left of this integration contour. Okay. And because we are taking these L's, the spatial components, to be real, okay, these poles never mix. Okay. So the positive poles remain positive poles, negative poles remain negative poles, because we do not have, this never vanishes. Okay. Okay. So these poles, which are to the right of K0 integration contour at P equal to 0, okay, must remain to the right all the way. Okay, because by assumption, we have, this is the first time we are hitting the pinch singularity. Okay, so we have not crossed, the poles have not crossed the contour. Okay, so they have to lie to the right of the integration contour. Okay. But now we see that this means that if we have a closed loop, okay, then for this loop momentum integration K, all the poles in the K0 plane are to the right of the K0 integration contour at the pinch, okay, because these are all the poles. Okay. And this means that the K0 integration contour is not pinched. Okay, so you can deform the K0 integration contour away from these singularities and have a different reduced diagram where this loop has collapsed to a point. Okay, and then you can repeat this argument, okay, to show that it is not possible to have a closed oriented loop inside a reduced diagram and still have a pinch. So the conclusion here is that a reduced diagram cannot have any loop along which the arrows are unidirectional. Okay. And from here, it's a simple graph theory exercise, or just you can do some mental exercise to show that this means, okay, that the vortices of this graph admit partial ordering, so the arrows flow from left to right. That we can partially order the vortices, so the arrows, all the arrows flow from left to right. Okay, this would not be possible if there are closed loops. Okay, but if there are no closed loops, you can draw the vortices so that arrows are going from left to right. Okay, this is also related to the another observation that if this is true, if there are no loops with where the arrow is closed, okay, then there cannot be a source or a sink in this graph. Okay, that every vortex must have some arrow going in, some arrow coming out. So here is an example of a reduced diagram that's allowed. Okay, there are no closed loops where you can follow the arrows. Okay, and indeed we see that the vortices have been ordered from such that the arrows always go from left to right. Okay, so these are the kinds of reduced diagrams that you can encounter, okay, along the deformation. Okay. But now let's consider a vertical cut. Okay, just a vertical line that passes through this. Okay. Total momentum that is entering from the left, from the external lines, is some P alpha, right? Because after all, where is the momentum coming from? It's coming from sum over momenta of external states. Okay, it's some P alpha. Okay, and let's suppose that L's are the momenta that are carried by these cut lines. Okay, the lines through which the vertical cut goes through, we call their momenta L1, L2, L3, etc. So we have the relation that P alpha is given by the sum of the LRs and P0 alpha is given by the sum of the energies. And this says, okay, just from this relation we see first of all that P is real, okay, because this is real, and it's above the threshold because it's the sum of the momenta carried by on-shell particles in the set A. Each of these particles are on-shell, right, because it satisfies L0 equal to square root of L square plus M square. Okay, these are in the reduced diagram, all lines are on-shell. Okay. So this contradicts the condition for the domain D. Okay, that if P alphas are real, okay, then you cannot have it must be then P alpha must be below the threshold. Okay, it's real and it's above the threshold because it's manifestly the P alpha can manifestly decay into a set of particles carrying this momenta and this energy. So this contradicts the condition for domain D, and this in turn means that we do not encounter a singularity during step 1. Now we come to step 2. Here the argument will be somewhat more involved. So let me try to see how far I can explain. So in step 2 we are supposed to deform imaginary P1 from 0 to the desired values. Okay. And during this deformation we keep all other components of the PAs fixed. Okay. And again it's up to me to choose the loop momentum integration contours as long as I can find one which avoids singularities. Okay. So we'll choose the loop momentum integration contours such that the K2 to KD minus 1, okay, these are all integrated along the real axis. K1 we cannot keep fixed along the real axis, so you have to allow these to be deformed away from the real axis, but the ends of course have to be fixed at plus minus infinity. Okay. And here is the non-trivial step that the integration contour along of K is 0. Okay. These will be taken to be the same as the ones that we get at the end of step 1. So you have already proven that at the end of step 1 there is some integration contours for the K0s, okay, which avoid singularities, which avoid pinches. Okay, that's the last part of the statement. We keep the K0 integration contours fixed at those positions. Okay. But of course, these contours depend on the other momentum, right? So we keep them fixed for fixed values of real Ks1 and Ks2 to Ksd minus 1. And our goal will be to show that by appropriate choice of the Ks1 integration contour, we can avoid pinch. Okay. And again, we will assume that we run into a pinch singularity, okay, and then show that there is a contradiction. Okay. So the next few slides will be basically focusing on the configuration that we reach at the end of the first step. Okay, don't deform anything as yet. Okay, but we will try to get a better understanding of that configuration. Okay, but now from the point of view of the Ks1 integration contour. Okay, what's happening in the Ks1 plane? Okay. So here what I have done is that I have plotted in the complex Ks1 plane. Okay. This is real Ks1, this is imaginary Ks1. The location of the poles with lowest imaginary Ks1 for given real Ks1, because there are many propagators, right? So this is the location for the lowest, the one that comes closest to the real axis. For every real Ks1, I have plotted the poles that come closest to the real axis, both from top and from below. These contours I'll call the singular loci. Okay. Now we know that these contours cannot reach the real axis, okay, because we have already proven, okay, that by taking the Ks1 along the real axis and by deforming the Ks0 contours appropriately, we avoid poles. So in the Ks1 integration contour, right, we know that there is no pole along the real axis. Okay, so the poles are away from the real axis. Okay. So we'll denote by LR the momenta carried by individual propagators that carry the momentum K, the loop momentum Ks. Okay, so basically Bs is the set of propagators through which Ks flows. So those are the propagators which will depend, whose momentum depends on Ks. So this is the general structure. Okay, that the momentum along the propagator is the loop momentum plus some LRs, where LRs are the linear combinations of external momenta and other loop momenta, okay, which are entering the vortex. Okay. And so the poles in the L plane, okay, are easy to understand. This is the same L square plus M square equal to 0 condition, but written now as L1 given in terms of the L0 and L transverse, where L transverse is from L2 to LD minus 1. Okay. And this is the formula. Okay, we'll come back to this formula again a little later. Okay, and we'll see the significance of this a little later. Okay. So right now, let me just emphasize one point, that at the poles, if you look at KS1 and LR1, okay, this is the relation. Okay. These have the same imaginary parts because these are all real. Okay, we are still at the end of the first deformation. Okay, we have not deformed the one integration contours, the K1 integration contours away from the real axis. Okay, everything is real. So the imaginary parts of LR and KS are the same. Okay. So here this is the same graph again. So this is a singular loci. This is, as far as the poles approach, the real KS1 integration axis. Okay. But we know that they do not actually hit the integration axis, because we know that at the end of the first step there is no pinch. So on the upper curve, imaginary L1R is positive because imaginary KS1 is positive. On the lower curve, imaginary L1R is negative because imaginary KS1 is negative. So what we are going to do now is to deform the imaginary PS. Okay, this is the time we start the deformation. And in that process, we will keep other components fixed and see what happens to the singular loci. Okay, these are going to start moving once the one component starts changing. Okay, when the imaginary part of the one component starts changing. So you see that in the L plane, their positions do not change, because the on-shell condition relates L1R to the transverse momentum and the zero components, and these, we have already said that their contours are not allowed to change during the second step. Okay. So these remain the same. But what changes is the relation between K and L. Okay, because of this relation, now L1R acquires imaginary part. Okay. And because of this, in the KS plane, these singular loci start moving up and down. Okay. So typically earlier the KS1 contour was integrated along minus infinity to plus infinity. Now what's going to happen is that some pole may come down and prevent us from integrating it all the way from minus infinity to plus infinity. Okay. But this is still okay because you can deform the contour and you can avoid the singularities. The problem comes here. Once some point on the upper graph and some point on the lower graph touches, then we cannot find a KS1 integration contour that starts from minus infinity, ends at plus infinity, and goes through. Okay, because it has to hit the singularity. But now recall that the upper graph had imaginary L1R positive, and the lower curve had this negative. This was at the end of the first step. Okay. And as I described here, that because of this formulae, okay, imaginary L1R is not going to change. In fact, the L1R itself is not going to change during the second step of the deformation. Okay, because this involves only the transverse momenta and the zero components, and those contours are kept fixed. So it is still true that on the upper curve, imaginary L1Rs are all positive, and on the lower curve, imaginary L1Rs are all negative. Okay, even though the imaginary KRs of course change, right, because they have been gotten shifted. So what does this show? This shows that in order to hit a singularity in the KS1 integration contour, at least a pair of propagators along the loop must have opposite values of imaginary L1R at the pinch. Okay. That at least one should have positive imaginary L1R, one should have negative imaginary L1R. And this must hold for every loop, because you can repeat this argument for every case, the momentum flowing along every loop. Okay. So this is again the same statement, that at the pinch at least a pair of propagators along any loop must have opposite values of imaginary L1R. Okay. And now we again draw a reduced diagram. Okay. But now we are going to put double arrows on the reduced diagram, okay, where the double arrows now show the direction of imaginary L1R. Okay. These are completely uncorrelated with the single arrows that we had earlier, okay, which then are describe the the sign of the L0. Right. Now we are drawing the arrows to denote the sign of imaginary part of L1R. Okay. And by this result, that at least a pair of propagators along any loop must have opposite values of imaginary L1R. Okay. Means that we cannot traverse a loop by moving along double arrows. Right? There is a closed loop with where you can follow the double arrows, because that will violate this statement. Okay. And then by the same logic, we can assign a partial ordering to the vortices, so that imaginary L1R flows from left to right. Okay, so a diagram like this, okay, where arrows flow from left to right. So now, again, let's draw a vertical line. Take the collection of propagators that this line intersects, okay, and you have the following relation. Okay. So P alpha, okay, which is the total momentum that is flowing from the left, okay, is sum over LRs. Okay, that's by momentum conservation. Okay. Each LR is on shell. Okay, we don't know which direction the energy is flowing. We don't need to know. Okay, but each LR is on shell, and what we know is that each LR has imaginary L1R positive, because all the arrows flow from left to right. Okay. And now simple kinematic analysis can show that this is incompatible with the P's belonging to the domain of analyticity, the primitive domain of analyticity. Okay, so let me just give that argument and then I'll stop. Okay, so let's say for given any quadrant in the 0, 1 plane, so this is a 0, 1 plane, Q0, Q1, okay, Q refers to some momentum which you don't care. We denote the 4 quadrants, V plus V minus are the time-like momenta, W plus W minus are the space-like momenta, okay, for any Q. Okay. So now let's look at these relations. Okay. First, this says that LR is on shell. Now, if you recall the argument that I gave near the beginning of the talk, okay, there of course you are dealing with external momenta, but it's the same argument for internal momenta, that if a momentum is on shell, then its imaginary part must be space-like. Okay. And if the imaginary part is space-like, then the fact that imaginary L1R is positive, look at this diagram. Okay, now you think of this as a imaginary L10, imaginary L11. Okay. If imaginary LR1 is positive, then imaginary LR must belong to W plus. Okay. Because this, so W plus and W minus are the two space-like domains, okay, and positive momentum comes in the W plus. Okay. And now P alpha is the sum of these. Okay. So if you add vectors inside W plus, okay, just simple inspection can show that the resulting vector must be in W plus. Okay. So imaginary P alpha is in W plus, which means imaginary P alpha is space-like. Okay. And that's of course incompatible with the domain condition that imaginary P alpha must be time-like. So the conclusion from here is that our initial assumption must be wrong and these are not pinched. Okay, because assuming that they are pinched, we arrive at a conclusion that we violate the condition of being in the domain D. Okay. So this in turn shows that the off-shell Green's function is analytic in the domain D. And of course, with this qualification that imaginary PL lies in a two-dimensional Lorentzian plane, okay, this proves the analyticity of the off-shell Green's function of string field theory in the primitive domain of analyticity. Okay. And then once you have proven this, then you can, it follows from this that all the results that we have for S matrix from the axiomatic quantum field theory are also valid in string theory, because that's where we start. Right? This is the starting point of deriving all the results for analyticity properties of the S matrix. Okay, so that's the end of the talk. So let me just end with listing some references. So these are references both for the earlier talk and today's talk. Thank you.
Questions? So somehow or other, the fact that when you do higher loop string amplitudes, you have to restrict to modulus, the function of the fundamental domain and things like that.
Yes.
This must matter for analytics.
Yes, of course. So that, how do you show this? Yeah. Okay. So that has of course gone into these vortices. Right, in the definition of the vortex, this knows everything about the modular invariance and so on. Right? This is a gauge fixed action, but you start with the gauge invariant action and then we gauge fix to arrive at this. So there, all the good properties of string theory goes in there, okay, in the construction of the string field theory. Okay. The property which is not manifest here, right, is the high energy behavior. Right? We know, for example, that if we have high energy behavior in string theory, then we expect a fall off. Right? But if you have a vortices like this, which have exponential of minus ck alpha square, then you can see that for large real energy, it grows exponentially. Right? And so that in string theory, that's repaired by the fact that there is cancellation between different Feynman diagrams, okay, which eventually makes it fall rather than grow. Okay? So the individual Feynman diagrams don't have good high energy behavior in the Lorentzian region. Okay? But that doesn't affect us in the proof of analyticity. Thank you.